I think we have talked about the flux and driving forces last time. And today I think we will talk about the membrane materials. Of course, you know that materials for this membrane could be mainly done by polymers so far, but metals, ceramics, biological substances could be also components for the membrane formation. In this case, we can think about the ion exchange groups or non-ion exchange groups or any chelating agents and complexing agents, so that depending upon the application or membrane processes, we will be able to select some of those materials. Okay? From now on, I think we can talk about a little bit about the polymers. For those of you who are not familiar with the polymers, then I think we will be helpful. But for those of you who are very familiar with the polymers, maybe boring. So I think by looking at your response, I will go fast or slow depending on your responses. Okay, polymers are regarded as a long chain molecules composed of repetitive linkages of small molecules known as the monomers. So if I have A as a monomeric units, A, and the molecular weight of A will be increasing. And the high molecular weight components are regarded as a polymer. Polymer is the same as macromolecules, so the molecule will become larger. That's a one molecule, okay, instead of just a small one molecule. Okay, so number of molecules will be decreasing, but the molecular weight will be increasing by the polymerization reactions. Depending on the monomeric units and how many monomeric units you have, we can classify it as a single homopolymer or copolymer or topolymer and so on. Homopolymer is the one that has only one monomeric unit in your polymers, but copolymer has two monomeric units. Topolymer has three monomeric units and so on. So now here we have, for example, A and B type of the monomeric units. So we can think of a copolymer here in this case. A, is a single homopolymer. AA, BBA, AA, BBA could be linearly linked, so that could be regarded as copolymer. But if I have a block of A and block of B, so if I have two blocks, two AAA, BBB could be connected to each other in linear form, we call that as a block copolymer. Graft copolymer is the one that has a one main chain composed of, for example, A, and if I have a second chain composed of B, then we call that as a branched copolymer or graft copolymers. Cross-linked structure is the one that we have all of those linear backbone that's connected to each other as a cross-linker. Okay? So the cross-linker is like a net structure, so we call it as a network polymer. Okay? The network polymer is although it's represented as 2D structure, actually this is a 3D structure. Okay? Three-dimensional network polymer structure is known as a cross-linked polymer. Now, polymer, we have a lot of different properties. Okay? We could have a crystalline structure or amorphous structure. Amorphous form is very important for your transfer properties because crystalline form is like a rock, and amorphous region is regarded as a transportable region, whereas crystalline region is a barrier region, okay? blockade region. So the crystallinity or flexibility, all those properties are influencing the transfer properties. in membranes. So we need to know more about this crystallinity and so on. Well, in some polymers, we have a tacticity. So for example, if I have a polypropylene where this al is methyl group, this methyl group could be arranged in one direction, so that's on the bottom of this main chain or the upper, whatever it is. It's called the isotactic polypropylene. We can have al as an alternative way. This is called the syntactic. If the al is in random form, there is any order, we call it as atactic polypropylene. Okay? Atactic or syntactic are much more flexible and amorphous than the isotactic polypropylene. Okay? So if you wanted to make a very thin film out of polypropylene, in order to be used as the carrier for the heavy metal, heavy stuff, then crystalline isotactic polypropylene will be much more plausible than the atactic polypropylene, because atactic polypropylene will be more flexible, so it will be stretched very easily, whereas isotactic polypropylene is much more crystalline, so that it resists its heavy weight. So if you go to a supermarket and when you buy your very thin packaging film, is that right? The packaging film, storage the plastic. Usually this is very thin and should be made of isotactic polypropylene instead of atactic polypropylene. Right? So how we can control this tacticity is another issue, but anyway, we have 3 different types of tacticity. This al could be methyl group, al could be chlorine, al could be benzene. If it's benzene, we have a styrene. So this is what we have, a polystyrene, PVC, PP. Many of those type of polymers could have a tacticity. We need to know about the glass transition temperature, but glass transition temperature might be different depending on the side chain group. Okay, if I have polyethylene, the Tg is minus 120 degrees C. Whereas if you have if you replace this hydrogen in the side chain al, if the R is replaced to methyl group, then because it's much bulkier, Tg increases. Further, changing from aliphatic to aromatic will increase the glass transition temperature and so on. The chlorine, the acrylonitrile, cyano group, or fluorine, stuff like that. So if I have if you replace this al with the small to larger or non-polar to polar side group, then your glass transition temperature increases. Now, glass transition temperature is important because if you look at this temperature versus the modulus curve, when you increase the temperature, your material was a glassy state. Actually, this is not gassy, but glassy state. In other words, this is in a solid state, but because you add your thermal energy to your polymer, your material will become a little softer because of the movement of your polymer chain. Now, when you increase your temperature, then your main chain, for example, if I have a main chain, like a tree, you have a trunk, and you have a branch. Okay, when you increase the temperature, you slowly increase your leaves first, perhaps because of the wind. If it's a wind, okay, it moves your smaller leaves will move. If you further increase, then a little larger chain will increase, like a side chain or so. And if I have a further increase, then my trunk, or if I have a typhoon, then the tree will be falling down. So it's the same thing, movement of your tree, similar to the polymeric units. So modulus or free modulus decreases as you increase your temperature. However, if I increase your temperature, then occupied volume in the space might be increasing because of the thermal movement. In other words, if I increase the temperature, then I need this much space. So this is the occupied volume, and this is the free volume. Okay, so this is the free. So I need extra volume to move my chain, polymer chain. Okay, and if I increase the further temperature, then I need occupied volume with the little larger free volumes. So free volume always increases as you increase your temperature. Anyway, modulus decreases because of the flexibility upon increasing the temperature. Now, there are two transition temperatures. First one is a glass transition temperature, and the second one is melting temperature. When your glass state or solid state melts, there is no storage modulus. So modulus will be drastically decreased. So drastic decreasing point of your modulus is called the melting temperature, and there is a phase transition between the solid state with the liquid state. Within the solid state, I may have a glassy region and rubbery region. Okay? When you think about the glass is very hard but brittle. So you have a high modulus, but if you think about the rubber, this material is softer, so that you have a lower, storage modulus. So but increasing the flexibility, but becomes tough. Okay. Anyway, both of those rubber state and the glass states are in the solid state. But there are some transition points, glassy to rubbery region. So high modulus, low modulus region, the transition point is called the glass transition temperature. You will see in next slide how the free volume will change between those glassy versus the rubbery states. Depending upon the type of your polymer, we talked about the amorphous polymer, like atactic polypropylene. We talked about the semi-crystalline or the much larger crystalline, polymers. Your rubbery region might be different. Okay, modulus of your material is different in the rubbery states. In the rubbery state, if your material is still in the high modulus region, we should have we think that there is no amorphous region, because the TG is more like a movement of amorphous regions, whereas melting temperature is the movement of your crystalline regions. Main chain moves at melting temperature. Main chain melts actually. Crystal melts, so there is no modulus here in this case. Now, if I have a crystalline and in between this crystalline and amorphous region, we call it as a semi-crystalline polymer. Most of the polymer that we are using, for example, textiles, fibers, are made of semi-crystalline polymer. Semi-crystalline is, this is a very ambiguous term in terms of the percent crystallinity. So we don't know yet how much the crystalline form, the crystalline portion is, but maybe it can range from 10% to 50% or 70%, something like that. So all of those ranges are called the semi-crystalline polymers. We can have 100% crystalline polymer or 100% amorphous polymer, such as a rubber in this case. Molecular weight is very important, of course. For those of you who are not familiar with the molecular weight, please go back to your polymer chemistry course textbook and think about it. In brief, you have when your monomeric units are gathered together to link to become a high molecular polymer, the molecular weight of one chain and second chain, third chain is all different. Okay? Although the monomeric units is the same, your molecular weight of each chain is very different. Not like low molecular weight components. Therefore, we have to think about the statistical way of describing our molecular weight of a whole components, and there are at least 4 ways of describing this the molecular weights: number average molecular weight, weight average molecular weight, the viscosity average molecular weight, and G average molecular weights. Okay? So you have a distribution of the molecules here in this case. So always we have broad distributions. So this is the molecular weight of each chain, and if we can count in the beaker, if we can count the how many molecules of molecular weight of 100, for example, then this could be this number. So this is the number of molecules. This is the molecular weight of each chain. Okay? So each chain may have a high molecular weight to the low molecular weight distributions, something like this. If I have a molecular weight distribution, something like this, versus the one that we have seen, we call this is the broad molecular weight distribution versus the narrow molecular weight distributions. Narrow molecular distribution polymer is preferred because you can predict your property of your material later on after processing your membrane or plastic or whatever. If I have a broad molecular weight distribution, then it's difficult to predict because high molecular weight components is expected to have a high mechanical strength. Low molecular weight component could be expected to have a lower mechanical property. Therefore, the property of each product, for example, this plastic, is a little different from the product that is made from this polymer. And also the processing parameter of making extrusion or injection, you have to think about the rheology and the viscosity and the flow of the fluid through those channels or nozzles is predictable experimentally or theoretically, versus a little bit complicated if you use this polymer in a melt system or whatever. So, but anyway, there are 4 types of molecular weights, molecular weight expressions. There the peak point molecular weight is called Mn, number average molecular weight, and the weight average molecular weight is always larger than the number average molecular weight. We may have a Z average molecular weight or viscosity average molecular weights. So there are 4 ways of molecular weights, and as your molecular weight expression is different, from Mn to Mz, its peak molecular weight is always different. So that means that Mz is always larger than Mn in many cases. MWD is equal to MW divided by Mn in many cases. If Mw and Mn is equal to 1, that means that your difference between Mn and Mw is the same. So for example, narrow molecular distribution may have a very small difference in between the 4 expressions. So in this case, Mn and Mw is equal to 1. Mn and Mw, Mn over Mw over Mn is always greater than 1 in this case. So MWD is an indication of the molecular weights. Now these days, we can predict this molecular weight very precisely using the light scattering detector in the GPC, so that we can calculate the Mn, Mw, Mz, stuff like that in a very different way. Usually, if you are not using light scattering, then we can compare the molecular weight of standard material, for example, polystyrene, of known molecular weight versus your unknown samples. So first, you have to prepare the calibration curve using your standard material polystyrenes, and then you detect your unknown polymer sample with unknown molecular weight. Okay. We have 3 GPC with the different the solvents, so that you can use your NMP GPC or THF GPC or water GPC, stuff like that. I hope you can purchase a light scattering detector later on. We are using our refractive index detector and UV detectors in most cases. There was a molecular weight, and this is the free volume. Okay. Free volume, as you increase the temperature, your specific volume increases in many cases, because as I mentioned to you, this is you have occupied volume, and your extra volume is necessary. So as you increase the temperature, you have extra volumes, and extra volume, the slope of the extra volume is almost the same in the glass state, although it's very small. But after the transformation from the glass state to rubbery state, you need another extra volume because of the change of your perhaps movement of your segments. So for example, in the glass state, perhaps your leaves might be moving, so the magnitude of your increase of your free volume might be the same. However, after glass transition temperature, perhaps some segments of your motion might be moving, so that perhaps your arm or maybe branch in your tree might be moving. So the magnitude of your increase is a little much larger, and after melting temperature, then everything's gone. So your free volume, there's no free volume though, but your specific volume will drastically increase in the case. Free volume, extent of free volume might be expressed in many the theories. So I think this is one of the free volume theory, I guess, here. So the free volume and specific volume can be described here in this case, where the volume, when the Tg is greater than the temperature of your detection in this glass region, then the volume is expressed in this way, whereas volume after this Tg is described here in this case. You see you have extra volume here in this term. So by looking at this curve, when Tg, so you knew in one of those tables in previous slides, In some cases, the Tg is in negative value, in other words, below 0 or above 0. So when you look at your material at room temperature, when your room temperature is here, your Tg is always lower than room temperature. So Tg is always here. Then your material is in the rubbery state. When room temperature is here, okay, the Tg is always greater than room temperature. So my material is in the glassy state. So you see where your room temperature is all about, then the material property might be different. Then the question is, when we go back to the slide here, we have, for example, polystyrene. Polystyrene, the Tg is about 100 degrees C. So at room temperature, if you think about the room temperature, you have a higher glass transition temperature. So your material, I'm looking at this polystyrene in the glassy state. So this material is glassy. Okay, all of those polymers are glassy, right? That's correct. So this is PVC is glassy polymer. The polyacrylonitrile is glassy and crystalline. PTFE is also crystalline, and so on. Polypropylene, polyethylene has a Tg in the range of -15 to -220. So this material should be rubbery, right? Should be rubbery. However, these materials are not rubbery. Not rubbery. Why? So I was wrong, right? My statement was wrong because Tg is negative. Tg is negative, so I'm looking at this material here in this case. Room temperature is here, so Tg is here. So this material should be rubbery material because polyethylene has a Tg of around -120. So I'm wrong. What happened?
I think polyethylene and acetate polypropylene have their semi-crystalline structure. So if two phase before phase, you can see the storage modulus graph. Semi-crystalline polymer is much larger than storage modulus, so we can have thick material. And these crystalline their regular latex and they lifting, so they are nearby segments. So I think these reasons can be
exactly. Jusong has an exact answer. Well, polyethylene, if you look at the structure, polyethylene has a linear structure, of course, but all is hydrogen, and this polymer is flexible, because you don't have any the side chains. If I have a larger side chain, then the carbon-carbon movement will be restricted. But if I have just a hydrogen, then carbon-carbon is tetrahedral, so it's rotatable in each chain. So it's very flexible. It should be rubbery. It should be rubbery, right? That's correct, -120. But because you do not have any substituent groups, you can stack those linear chains together to form crystals. So the crystallinity will influence the polyethylene, not the rubbery form at room temperature. Okay, so crystallinity will make a little bit of difference in the material form in the case. Okay, let's talk about the membrane itself. When when we are talking about the membrane separation process, separation process is important too, right? Whether you are applying the gas separation or, well, if you're talking about the liquid separation, maybe evaporation or membrane distillation or desalination of using RO, stuff like that might be, feasible, but membrane itself, membrane property, material with the properties that we have already talked about are very important too. So membranes are key issue in membrane separation processes. So we need to know about the structure, we need to know about what kind of functional groups that they may have, whether we have ionic groups or charged groups or not. And we have to think about the mechanism of the transport too, whether we have to apply the driving force as a pressure gradient or temperature gradient, electrical gradient, stuff like that. And material itself are also very important too. There are many ways of making membranes. Sintering means increasing temperature, heat treatment. Right? Heat treatment, irradiation, phase separation, deep coating, sintering plus gel method, emulsification, charge group, and so on. So we will see each step later on. Also, the characterizational method, characterization of the membrane is important too, in order to study about this morphology and so on. So the characterization technique, for example, if I need to know about the pore size, there are many ways of determining the pore size of your membranes. Whether you need the gas to determine your pore size, or liquids, what kind of liquids that you are using, stuff like that will be important factor to determine your pore sizes. So characterization technique will be touched after this chapter 2. But membrane structure, membrane material, application are 3 very important properties too. If you are talking about the membrane itself, that means that it should be made of material, whether it's made of polymer or inorganic or whatever, metals. Whether we need the porous structure, asymmetric structure, denser structure, what kind of application, RO, gas, PV, or UF, MF, and so on. So, but in many cases, membrane materials are determining the application in the case of gas separation, because we are using dense membrane. And dense membrane is usually used to apply it into evaporation, whereas the membrane structure is much more important for porous membrane separation processes like MF and UF. Selectivity is often called the pump selectivity or the selectivity, and this is coming from chemical structure or the physical property of the membranes. Chain flexibility, of course, is a determining factor for permeability. In other words, how flexible the material, like a rubbery polymer or the glassy polymer. Rubbery polymer is flexible, and those flexible chain will determine the permeability, but permeability also influences the selectivity, because it's in the inverse relationship between these 2 properties. So if I have a flexible chain, selectivity goes down. Usually the CC, single bond, is flexible than the double bond in the main chain. So if I have a double, like a polyacetylene, it's much more rigid than the flexible chain like here in this case. If I have a side chain, Side chain always reduce the rotational movement so that it becomes a little rigid, increasing the glass transition temperature, lowering the free volumes. So all of those will influence the pump selectivity, of course. Permeability, as I mentioned to you, if I have a little bit of a porous membrane, permeability increases. Dense membrane, permeability goes down, but selectivity goes up. Glassy polymer, rubbery polymer, in between these two, the interface, we call the temperature will be defined as the glass transition temperatures. I mentioned to you the importance of your crystallinity in the case of polyethylene, of course the polypropylene too. Thermal property, chemical properties are in many cases important. So we need to know about the solubility aspect. Particularly these days, I haven't put any slides here in organic solvent nanofiltration, but in the case of nanofiltration, traditionally they were thinking of removing the divalent ions from the wastewater, applying the little low pressure, then reverse osmosis. So nanofiltration application was for wastewater treatment of specific ions in the cases. However, these days, for the last 10 years, nanofiltration technique has moved to the little high-valued chemical separation process, like separation of drugs, separation of isomers, separation of high-value chemicals from your chemical production industries. That's what we call organic solvent nanofiltration, or OSN, what's the other word?
Solvent resistant.
SRN, yeah, solvent resistant nanofiltration membranes. And Professor Andrew Livingstone at Imperial College is a world expert in that OSN area, and he's a pioneer, I guess. And Dr. John Kim here in the back in the class received a PhD from Livingstone's group, and receive his PhD about this OSN. So I think we can have an opportunity to introduce about the OSN later on. But anyway, organic solvent resistant or solvent resistant nanofiltration membrane requires chemical resistance to specific chemicals. In the case, we need to know about the chemical stability, right? Chemical stability, or if you're thinking about the thermal, high temperature operation of your membranes, like membrane operation at 100 degrees C or 200 degrees C or even 300 degrees C, there are not many choices of your polymers. So you have to think about the glass transition temperature of your each membrane material in order to select the right material, membrane materials. So the thermal property are also very important in this case. Usually the aromatic ring has a rigid chain. Aliphatic ring has aliphatic chain provides you flexibility. If I have a high stability, then processability might be an issue. Because processability and stability is a little bit opposite, right? Depending on the size of the pores, we can have a little different the strategies to make a membranes. But this slide shows whether you have a porous structure or a symmetric structure, or the symmetric polymer or asymmetric polymer, or if I will use inorganics, stuff like that, and depending on the techniques of making membrane, then the application might be limited to. So first of all, we need to think about the sintering first. Sintering can be described here in this slide. And if I have a particle, okay, if I have a powder, those are three circles like a powder, and increase the temperature, then those powder might be aggregated to each other or agglomerated each other to become the same volume, but this will be connected to each other. Okay, so this is what we call the sintering. For example, metal powder, like a crystalline metal powder, crystalline ceramic powder, will be melt each other at high temperature. It's not 100% melt, but heat it up to the agglomerated temperature or sintering temperature, then this will be connected to each other. Usually, when I have a stainless steel or tungsten, then we can have a sintering here in this case, ceramics, graphites, glasses even. We can even make a sintering or heat treatment of the crystalline polymers like polyethylene, crystalline polymers like PTFE, crystalline polymers like polypropylene. Okay, so if we heat treat it, then we can make a little different property of the materials. So after sintering, pore size will be a little smaller. So using these sintered techniques, we can apply this material in the other applications like removing or filtering the suspensions, gas separation, or radioisotope the separation applications too. In the case of PTFE, PTFE has a glass transition temperature of around 120 degrees C, as you have seen in this slide. But melting temperature is around 320 or something like that. So PTFE powder, okay, if you have a PTFE powder, okay, and if you increase the temperature close to melting temperature, or above the melting temperature, then it melts. And when you extrude those melts, and if you stretch them, cool them and stretch them, then the membrane looks something like this. So it looks like that each connecting points is an aggregated structure, agglomerated powdery structure, whereas a fibrous structure is like a connecting chains. So white color is a PTFE stretchable fibers, whereas black color is more like a pores. So you can see the porous structure of this PTFE by stretching, melting and stretching. Or this is what they call the. So anyway, using this porous structure, you can make a Gore-Tex. You can make a Gore-Tex. You can make a PTFE film for the membrane contactor, membrane distillation application, membrane crystallization. You can make a fabric coating. You can just use your the membranes as well. So vapors or gases will be easily moved through these pores, whereas the liquids, if it contains water, it cannot go through because of the hydrophobicity of these fibers. Okay? So when I look at the application, brochure, advertisement brochure of the Gore-Tex, you have a hot coffee, okay, maybe half filled, half hot coffee, and you have vapors, okay, vapors, and you can take a very nice picture of those vapors flowing, I mean, you know, evaporating from those hot coffees. But if you put your Gore-Tex on top of this and flip over, then there's nothing comes out, okay? Whereas if you just put it on top of it, this hot coffee, only the vapors will come out, just like the same as without any Gore-Tex. So this principle, you can, if we have a Gore-Tex coated outdoor, you know, shots, then of course this hydrophobic layer is a protective layer for water repellency. So the rainwater will not go inside of those fabric, whereas the vapors that is generated from your physical you know, activation of your body, the vapor will be going out, so you feel much more comfortable even in your movement. So that's the principle of your Gore-Tex, and this Gore-Tex is they use this PTFE, of course. So Gore-Tex is more like a spin-off company from DuPont. And these days they use this Gore-Tex technology to even to the shoes. So I know the Italian company called GOEX or something like that. They coat the outer shell of your shoes made of Gore-Tex, so it feels much more comfortable. If you think about your, you know, aspiration aspect of your shoes, so it's very expensive, much more expensive than the normal you know, shoes. So that's the application of this PTFE membrane. And this PTFE membrane is made of course, sintering. Second way of making the membrane, the porous membrane, is a track etching method. There are two-stage processes. First one is the ion beam bombarding of your films or membranes, and then second step is the etching process. When we have a film, such as a polycarbonate or polyethylene terephthalate, where although you know, that's very hard, it could be amorphous or it could be crystalline. But if I have a very strong film, then we can make a hole. We can drill these holes using this the irradiation method. What it is that it's like a laser, you know, the ion beam, the high energy ion beam is bombarding to the moving films. Okay? So it's continuously exposes to these you know, films, and this exposed or unexposed or damaged. If I have a damaged track here, you know, the little darker you know, blue color is the pathway of your ion beam. So I have you know, damaged area versus the non-damaged area here. Of course, there's nothing happened. You know, physically after this bombardment. But if I put this film into the etching solution, such as sodium hydroxide or very harsh solution, then this you can etch this the exposed area, so that this you know, the blue colored area will be gone, making a porous structure of your membrane. So you can see this porous structure later on, starting from very, you know, dense film. After these two processes, we have polymer that is etched, that has holes. So you see, it looks like a, you know, drilled drilled membranes. Now, this is quite messy. This looks messy because there is no uniformity in terms of arrangement of your holes, but the advantages of this type of track etched membrane is that you have a very very fine and very exact pore sizes. So you can utilize those pore size in separating the proteins, in separating the biological applications. So usually this track etched membrane is used in hospital in many cases. So millipores, they are using this type of membranes in biological applications. We are not using, in many cases, this track etched membrane in our chemical industry and so on, but in hospital, they need many filters. Small filter, of course. Small filter costs a lot of money, and this is the way of making their track etched membranes. You can have a dynamic membrane. Dynamic membrane could be utilized. I think Professor Drioli was an expert in that area. Looks like they have already done and published back in 1975, and authored with the Lonsdale and the Push. Lonsdale was a founder of Journal of Membrane Science. Okay, he's also a founder of Bend Corporation, membrane company located in Bend, B-E-N-D, in Oregon. Okay? So that was very famous at the time. And Push is a German scientist in I think it's Max Planck. And this Professor Push had a traffic accident back in the 80s, so he's not here anymore. But anyway, they have perhaps they have a collaboration when they were young, okay? And they have already done this dynamically formed membranes. What it is that they can control this pH and concentration of this aluminum, so and hydrolyze this product of aluminum, so that they can make they can make a membrane along with the reactions. Okay? So this is what they call the dynamic membranes. Fourth way of making membrane is by using phase separation. Phase, from liquid phase to solid phase, or solid phase, liquid phase, stuff like that. So we use phase changes, phase inversion, usually from liquid to solid phase transitions. And this has been the most versatile method of preparing the membranes. And by using this phase transition, phase inversion, you can modify, you can make a membrane porous, you can modify your porous structure from finger structure to sponge structure, sponge to finger, or dense structure of your skins and so on. Everything could be controlled by knowing the theory and aspect of this phase inversion. Usually, when you have a polymer, for example, if I have a polymer, and we need to dissolve this polymer in some solvents. So we need to choose the right solvents. Later, we'll talk about the importance of the green solvents, but let's talk about just the normal solvents like polar aprotic solvents like NMP or DMAC. Now, we can think of three very important polar aprotic solvents like NMP, N-methylpyrrolidone, dimethylacetoamide, or dimethylformamide. But toxicity is very high for DMF, dimethylformamide, and so DMF should be, I think it's already been banned from using this DMF in preparing the membranes. So please be careful about using DMF when you are using in the laboratory, because it's been known as a carcinogen. NMP and DMSO are okay so far. DMSO, dimethyl sulfoxide, are even used in making the patch for your, patch. In other words, if you formulate the drug with the adhesives along with the solvent and put the coat on top of the fabric, you can make a pus. We call that as a pus, the Shinshin pus or tail pus, something like that. Anyway, that was, they can relieve your pains, okay, if you apply your pus. Of course, you have a little bit of smells, but anyway, that's one way of drug delivery system, okay, through the skin layer. Or if you change your drug, then and apply it here in top of here, the product, Korean product name is called the Kimite, and under your ear, then that can release the pains when you are moving, when you're taking your ship, okay? Or onboard pain or something like that. It's called you can utilize the kimite, or you can use your hormone, particularly the lady's hormone, female hormone, for those who has pains during those periods. So they can put those patches in here, and there are many patches. And in order to make those patches, usually they use solvents to mix drugs with the adhesives. Okay, because usually the drugs are crystalline, so they have to put those into the solution form. And you cannot use the water, of course, so they use a little bit of solvents. That's in many cases DMSO, dimethyl sulfoxide. Anyway, NMP is quite popular here in preparing the membranes, but NMP is still toxic. So they wanted to, particularly in Europe, they wanted to replace this NMP with green, much more safer solvents. Okay? So we will talk about that later on. But anyway, we have a polymer, we have a solvent. So polymer and solvent interaction causes this two component into the one phase, which is the liquid phase. We call it as a polymer solution. But if I have a water, put those on top of this polymer solution, then it still slowly forms the precipitate. Okay, slowly forms the precipitate after some concentration of your non-solvent. So polymer, solvent, and non-solvent create some sort of thermodynamic aspect, and you can describe this interaction between those three components in Gibbs free energy. So if you think about the Gibbs free energy, then G is equal to enthalpy H minus T times entropy, TS. And the difference between these two components, like a polymer and second component, whether it's a solvent or non-solvent, is called delta G. Okay, so delta G is equal to delta H minus T delta S. So for polymer to form a solution, when the polymer is forming the polymer solution at the condition where the delta G is equal to negative, right? So delta G should be negative in order to form your polymer solution, because not because, but that delta G is it should be negative. If the delta G is equal to 0, that means that you have equilibrium between your solution versus the solid. So when you drop your non-solvent to the polymer solution, you can see the point where it starts forming the precipitate, and that's the point where the delta G is equal to 0. So that's at the equilibrium stages. So before that, before the polymer solution stages, your delta G between polymer and solvent is negative, right? So when the delta G is negative, then delta H should be negative, can be negative, or delta S should be positive, much more higher than what it is. So if you store them, then you can increase your solubility anyway. When delta H is negative, when delta H is negative between the polymer and solvent.
Then entropy of system.
Well, we are talking about enthalpy, right?
So in this relationship between delta H and delta S, right? So when delta H is negative means the delta G also negative should be.
Well, delta H. Actually, the enthalpy of each component, like a hydrogen, like a polymer and solvent and non-solvents, the interaction, that's the interaction between the polymer and the solvents.
Enthalpy is basically
When-
heat-based product.
Right. So when the polymer interaction, solvent interaction, we have to think about the polymer and solvent interactions. So when delta H is negative, then interaction between the polymer and solvent is prevalent than each interactions, right? So when enthalpy is positive, in other words, then means that you can form the precipitates, because polymer interaction, solvent interaction is much more higher than polymer and solvent interactions. So that's the relationship between the enthalpy between those polymer and the solvent phases. Anyway, you can think about those polymer and solvent interactions, and can express that in thermodynamic terms. Well, there are some words: polymer rich phase and polymer lean phase. Polymer rich phase means when we will be talking about the thermodynamic phase diagram, we will think about the polymer, solvent, and non-solvent scenarios. When you are talking about much more polymer, toward the polymer phases, then we call this polymer rich phase. When we have a lower polymer concentration region, then we can say that this is the polymer lean phase, polymer less, or polymer lean phase. Polymer lean phase will form your porous structure. Polymer rich phase will form your much denser structure. So that's why this is very important. Well, in phase inversion technology, we have various types of phase inversions. In this case, we can induce a phase inversion by evaporation of the solvent. We can make a phase inversion by vapor. We can make a phase inversion by the temperature difference. We can make a phase inversion by non-solvent. So there are 4 ways of making the phase inversions. Usually, this 4th method and the 3rd methods are very popular to make the membranes. So we will focus our work, our discussion about these 2 methodologies: non-solvent induced phase inversion, phase separation, called NIPS or TIPS, temperature induced. Okay. Okay, so let's talk about the each other, and then we can focus more on the TIPS and NIPS. EIPS, EIPS, evaporation-induced phase separation. Let's look at the scheme here. When you cast your film, solution of your layer, remarked as yellow, then after some time, you evaporate your solvents, then you make a film. Actually, you can induce the phase from solution phase or liquid phase to polymer rich phase or solid phase. So you change your phase as a function of time or by evaporation. So they call this as EIPS. Or we can just say this is a solvent evaporation rather than phase separation. That's easy way of making. Second ways of inducing phase separation is called the VIPS, VIPS. What it is that you cast the film of solution of your on top of the glass plate or whatever, then you can evaporate. If you evaporate, then that's EIPS. However, within the closed chamber, when you apply your vapor, water vapor, for example, water vapor, then that's a little different from the first case. Okay, when your water vapor is coming down, then water vapor, particularly the water, is usually the non-solvent. So water vapor will induce this phase separation or accelerates the phase separation, which is different from the first cases. And you make a little porous membrane in this case. Now, VIPS, VIPS, although it's interesting, there is no membrane that I know made of this VIPS in commercial scale. You can make a membrane in the laboratory scale, but it's very difficult to make a closed chamber and control the water vapor activities and water vapor, concentration, stuff like that. So in a larger scale, in fact. So usually in membrane manufacturing process using NIPS, they do not like water vapor. Okay? So water vapor, this VIPS could be the one that may have a high RH, high relative humidity region in the case. But so far, membrane producers do not like the water vapor. So always membranes are produced in the region where you have a low RH in the environment. So for example, in the United States, they need naturally the low humidity region and constant temperature. So in that region, you do not need any additional facilities to control those environments. So particularly the San Diego area, which is close to Mexico in the West Coast, the south of the LA, that's very preferable region. There are many membrane companies, manufacturing companies there in San Diego. But other than that, I think this is a little complicated. TIPS is the one that you utilize the temperature. So you spin or you make the film, the solution casting at high temperature. When you decrease the temperature, then you induce your polymers, crystallization and so on. So this is what we call TIPS. So temperature, high temperature to low temperature will induce the phase separation from, liquid phase to solid phase. And we have a TIPS hollow fiber membrane machine and flashing machine and upstairs, TANS4. So we can show you later on, and I think Seok-Young or Jun-Tae can show you the TIPS machine later on. NIPS is a non-solvent-induced phase separation. You make a membrane and put it into the, you make a solution coating on top of the glass plate and put it into water. Usually this is the non-solvent. So non-solvent and solvent in the solution will be exchanged each other. This is what we call the non-solvent-induced phase separation. So we will see how we can make a membrane actually in more detail about, particularly about the TIPS and NIPS next time. Usually by evaporation, you can make a dense film. And we can have a polymer, for example, this is the PEEK, but any polymer could be dissolved in solvent. Usually the solvent was a chloroform in this case, and when you cast and evaporate the chloroform, you make a dense film. You can have a porous film, porous membrane by inducing the water vapor. So this was one of the examples in the laboratory membrane scale. You can utilize this technique by replacing the polymer to a polyether sulfone or PVDF or polyamide with the same technique. So this is a little different structure than a track etch or the sintering techniques. Okay, so far I think we've talked about membrane materials to the membrane preparation methods. Particularly we are talking about the phase separations. Next time we will talk about in more detail about the phase separation. Particularly you can see how we can spin the fiber and porous structure, stuff like that, and we can talk about some theoretical aspect of phase separations. Okay. Any questions? Okay, have a nice weekend and see you in next Wednesday.